G'day everybody and welcome back to the channel. I'm going to start a new video series. This is the first video of the series. It's going to be a little bit similar to what Inside Guy does with Chip of the Day, it's called, I think. Yes, Chip of the Day. I'm going to do something different though, because I don't believe in copying people. What we're going to do is we're going to take a look at components that have interesting functionality to them and basically have a look at the component, have a look at the data sheet, build a test circuit up, and then we're going to look at some more interesting uses of the component. So basically it'll be a video series where there'll be different videos on different components, but there'll also be multiple videos on the one thing. So we might, I'll give you an example. We might take, say, a TL431 and make just a few standard circuits like a shunt regulator, series pass regulator, a few things like that that you probably find in the data sheet. And then we might do something interesting like build an audio amplifier out of a TL431, which is something you can do. You know, it's the more interesting things that I want to look at. But yeah, the other thing I want to do is I want to keep the test circuits built up for a couple of weeks. So if anyone knows of another interesting use for the same part, you can leave it in the comment section down below, and I'll be willing to try your suggestions too, and obviously video that as well. So that's what it is. So without further ado, let's get into it. So the chip I've chosen for today to start is the mc34063a. It's an inverting regulator, switching IC, whatever you want to call it. The thing that's good about this IC is its duty cycle is not limited, so that you can actually set it up for buck or boost. So that's always good. If you want to have a read of that, just pause the video and have a read. Some of its key features: 3 to 40 volt input, low standby current, current limiting. The switch inside it, the transistor, can do up to 1.5 amp. It's obviously adjustable. It can go up to 100 kilohertz. We'll discuss that a bit later, because the first test circuit that we're going to do actually only runs at about 40 kilohertz. So we'll discuss why that is. Precision 2% reference. I'm not sure. I've got some other switching ICs that I've built flybacks and like out of, and I'm not sure the precision of the references in them, so I'm not too sure how good that is. It's fairly good. It's not bad, but there are probably other quite common chips that have got more stable references that might be 1% or 0.5%, you know. Anyway, there's some more specifications, pinouts for different packages. So here we've got the first hint at something to do with the frequency. So about the phone, I'm trying to hold the phone in one arm. You know what? Let me see if I can set up a stand. I don't have anything set up yet to aim the phone at the screen without holding it. I should work on that. All right. So here we can see that there are different ways of actually setting it up with an external switch, that is. The little note actually says, if the output switch is driven into hard saturation, I'm not blocking my microphone, no, sorry, non-Darlington configuration at low switch currents, less than 300 milliamps, and higher drive currents over 30 milliamps, it may take up to 2 microseconds to come out of saturation. This condition will shorten the off time at frequencies above 30 kilohertz and is magnified at high temperatures. This condition does not occur with a Darlington configuration, since the output switch cannot saturate. If a non-Darlington configuration is used, the following output drive condition is recommended. which is where we put a resistor here. I don't know why that is drawn the way that is drawn like that, but I'm pretty sure that does not connect halfway on the end of the inductor there. That's funny. Ooh, jeez. Okay, I need to hold this with 2 hands. How am I going to use the mouse? I'm going to have to build a stand. Buy a tool tripod or something. Anyway, here's our first circuit that we're going to look at. This is a step-down converter. Our voltage in can be... Wait, that's not the circuit that I built up. Somehow I've got the wrong circuit up here. Oh, sorry, this is the first one. This is the first circuit that we're going to look at. So the input voltage can be from 8 to 16 volts. And our output voltage will be 28 volts. So let's go have a look at that. We're also going to have a look at it on the scope and have a look at the additional pi network and have a look at the difference that makes. All right, we're back at the bench. So there's the circuit built up. What I've done is, in advance, I've soldered a 330 microfarad capacitor to this probe, one of my modified power supply probes for working on power supplies. And the other one, because I've got 2 of these, is soldered to this little pi network. This is 100 microfarad and 1 microhenry. So everything here is exactly as suggested in the data sheet. We're using the exact data sheet values, voltages and everything so that we can compare it. Now, I will warn you in advance that it's pretty hard to trigger on this because of the way it's running on the breadboard, but we can have a look at the signal and we will see a massive reduction in noise. So that's our 330 microfarad capacitor in there. And that's, well, that's ground. And that's power. I'll bring a meter over here as well. Let me just adjust the scope first. I'm already off to a great start. I just bumped the breadboard, which is not something you want to do with circuits like this. And you guessed it, popped the chip. Thankfully I've got plenty of them, but still, I mean, I've only got 8 left after this one. I'll do this off camera. Alright, the new chip is in. Just put that over there. Pretty sure it's the chip I blew, we'll see in a sec. I'll put a multimeter here as well so we can look at it. Yep, we're up and running. Okay, so the data sheet says expect 400 millivolts peak to peak. The scope says that there's 300 millivolts peak to peak. Now that's because I've got a good probe, so we're actually seeing what's actually coming from the circuit, and I've laid this out the best I can with a breadboard for a switching converter, and I've used quality caps, so that's probably why. So what we're going to do now is we're going to put the suggested 1 microhenry and 100 microfarad cap and add that to the output, and then we're going to measure that. So to do that, I'm just going to unplug that probe, but leave it attached. I'll take the multimeter off, and as you can see, I've already got a wire running out from positive over here. So we can just take this and put it in between ground, an empty track, and the track with the positive wire in it. Alright. And I'll move this over to the second capacitor now. Alright, let's power up. Alright, we're powered up. I forgot to plug the second probe in. I'll just do that quickly. Alright. This is kind of hard to trigger, like I said. So I'll just do a single shot. And we're down to 86 millivolts peak to peak, and a much smoother looking waveform. And if we look here, it says 40 millivolts. Look, that's fair enough. We are on a piece of breadboard. The breadboard's got inductance, it's got capacitance between tracks, it's got resistance on the connections. It's really, really bad. And circuits like this have got really high current pulses on the edge of the switching. So, you know, this will be ringing and doing all sorts of crazy things. In fact, if I got a probe and we had a probe around here, I probably wouldn't be able to trigger on it. It would be that messy and full of noise and artifacts. So there you have that. So I'm going to go set up another board. Well, first I'm going to put this in the bin because it's definitely dead. Okay. And now I'm going to set up for the step down converter, and we'll take a look at that. Now I've already got these components here ready, but I've been thinking about this. The step down converter, they want to use a 470 microfarad cap. I'm just going to leave the 330 that we've got on here. It just means that our noise results are going to be slightly higher than what the datasheet says, but I'm not going to bother swapping around the capacitor. Also, the 0.22 ohm resistor that is required for this circuit is a 0.33 ohm for the other circuit. That's why that's there. And that inductor is a 220 microhenry, and that's a 220. I didn't have a 180 lying around, and I couldn't be bothered winding one. This will do fine for the purpose of this experiment. And yes, as I said that, I just realized how silly that was. You see, I set this up last night and I grabbed the 100 mic inductor and the 220, and I started to wind one as well, but I couldn't. The wire I chose, I'll just show you. Oh, I've grabbed the wrong drawer, my apologies. So the one I started winding last night, the wire I chose was way too thick, and by the time I got up to over winding it, I still was way shy of the inductance I needed. So I ended up just using a 220, but this morning for some reason I grabbed another one when I thought I was going to set up another circuit, not realizing that was the same inductor. Haha. Okay, I've laid it out again, but for the step down circuit. So I'll start by putting the multimeter on the capacitor. I haven't tested this yet, so if I've done something wrong, you'll get to see. This second network's not hooked up. What I've done is I've just put the two grounds in the ground tray so I can just add a wire to the end of the inductor and the positive of this output, and then we can compare without having to mess around with it basically. Let me just put a couple of wires in for power because I forgot. I'm happy with that. Now this is quite tight, so a lot of things could touch, so I've got to be careful, but I wanted to keep the layout good for what it is. So let's see if this works. Oh, what's my input voltage? Okay, input voltage should be 25 volts. So let me go from 12 to 25. Alright, we've got 25 volts. Our output voltage, sorry, I haven't even shown you guys the thing yet. Here we go. So this is the step down circuit. As you see, we've got a 0.33 ohm instead of a 0.22. We've got some different resistor values and just a different way of constructing the circuit in general. Here we're rated for 120 millivolts peak to peak at 5 volts. And apparently when we add the second network, we can get down to 40 millivolts peak to peak. So let's go give that a look at. All right, applying power. Well, the circuit works, so that's good. Let's go to the scope. Looks like we're doing pretty good already. That's 86 millivolts peak to peak. And remember, that's only a 330 microfarad capacitor on the output. But at the same time, this circuit is unloaded. Alright, let's go put our link in. Oh, hold on. No, I've got the wrong probe plugged in. We were just looking at... Oh, I'm a dumbass. Anyone spot that? Let's do that again, shall we? Silly me, silly me. Okay, so 5.3 volts, and yeah, we're still doing good. It's 100 millivolts peak to peak. All right, let's add our second network. I'll swap over the probes and power up. Now we've only got 34 millivolts. Actually, I'm going to have to adjust. Hold on. So yeah, 30 millivolts peak to peak. Quite nice if you ask me. Alright, so in this data sheet, sorry, I'll take you back to the data sheet. In this data sheet there are some other things that we can do, like we can use an external transistor as a switch, saturated or unsaturated. We can build some different circuits, like a voltage inverting converter. We've got some PCB layout ideas. So that's where I wanted to bring you guys into this now and say, if anyone wants to see something done with this, you have an idea or something like that and you want to try it out and see if it's doable, leave it in the comment section. I'd be more than happy to do that in a following video. Anyway, that's all for this video. So leave it down below what you think and give me a like and a sub, and I'll see you all soon in another video. Thanks for watching.